Hello guys, so in this video let's talk about physics. So basically we'll address the history of physics, we'll discuss in short, and then I'll talk about the future of physics, why am I still hopeful about the future of physics, and some of my insights about physics in general, the development of physics in general. So basically let's start with the first thing is that if we look at the history of physics, it all began with Sir Isaac Newton. Actually it began even before Isaac Newton, but he's the one who first saw some regularity, some pattern in the world. He saw some similarity between a falling apple and the moon, and then he discovered the gravitational force, and then he gave the laws of motion, which is applicable to all bodies in the universe, not just an apple and the earth. And then he gave three laws which are applicable to almost all systems at the macroscopic level. And then what Sir Isaac Newton, the greatness of Newton is that he is the pioneer of both physics and mathematics, and lot of fields in mathematics. He developed the mathematics required to build his physics theories parallelly. And then but then it was discovered that there are four fundamental forces in nature. Like what are forces? Basically in the classical view, force is just the interaction between particles. The force is the kind of the cause of the changes we see around us. Now, so then naturally the question arises, how many different types of forces are there? And then some people said, like, then it was discovered that there are a lot of forces we see, but they can all be categorized into four fundamental categories. Like, of course, if I push the wall and if I kick a ball, they're the same kind of force, but they look different. But they're all the example of electromagnetic force, because there's a kind of electromagnetic interaction between my hand or my foot and that object. Then if I jump and I fall back, then that is an example of gravitational interaction, which is fundamentally different from electromagnetic interaction because of a lot of reasons, right? Gravity is always attractive, unlike electromagnetic magnetism. And then there is no concept of positive and negative mass in gravity, but there is a concept of positive and negative charge in electromagnetism. So basically these are the different forces. There are four fundamental forces in nature which has been discovered over a lot of years, not in Newton's time, over the course of years. And naturally people were confused because especially a lot of great physicists, including Einstein, they found it difficult to believe that how can nature be based on such an extravagant design? Like there should be one fundamental force. There can be different manifestations, but why four fundamentally different kind of forces in the universe? That is the question that bothered Einstein. In fact, in Einstein's time, there were only two forces that were known: electromagnetism and gravity. The weak and strong nuclear forces were discovered a bit later, but Einstein couldn't even accept the existence of two different forces in nature, and he devoted almost the last 3 decades of his life to build a unified field theory. He tried to describe both of these forces in the same theoretical framework. And there are a lot of similarities between gravitational force and electromagnetic force, but they could not be successfully reconciled. I mean, they could not be successfully described in the same theoretical framework, not even today. The story is a bit complicated, but let's just discuss in brief, right? So basically, then after Einstein, it was found out. See, basically, what is electromagnetic interaction? It's basically nothing but electromagnetic wave, light. What we see as light, it's nothing but an electromagnetic wave, and which it's kind of ripples in the electromagnetic field. So electromagnetic theory has a field concept in it. And then gravity in Newton's view, gravity did not have a field concept. It was just a force between two masses. But Einstein changed our worldview, changed our knowledge of gravity, our understanding of gravity, with his great general theory of relativity, which till this date remains one of the two pillars of physics. So according to general relativity, gravity is not it's not the main thing. It's actually just a consequence of the curvature of space-time. So in special relativity, Einstein brought space and time into the same footing, and then there is a four-dimensional world around us, which is the four-dimensional space-time. Our world is basically, in Einstein's description, the world is four-dimensional. There are three space dimensions, and he treated time as the fourth dimension. I'm not going into the mathematics here; it's a bit complicated. But the thing is that in special relativity, Einstein kind of unified space and time into this something called space-time. But special relativity, why is it called special? Because it deals with some special phenomena. It's not. It deals with only inertial bodies and non-accelerating reference frames. And we can study accelerated motion in special relativity. But the observer should be moving. There is a fixed reference frame, and the moving reference frame should be moving at a constant speed with the fixed reference frame. That is the constraint in special relativity. But if we try to generalize this, then we get the general theory of relativity, which is pretty complicated mathematically. But the idea is that general relativity explains the force of gravity. Gravity arises due to the curvature of space-time. this, because it's just like when we have a massive body. Massive body means a body with some mass. Then it distorts the space-time around it, and the space-time gets curved, and it's a kind of, due to this curvature of space-time, the motion of the other bodies also, other nearby bodies also gets affected. And this way Einstein could explain why the earth moves around the sun and all, and in fact everything, like an apple falling down to the earth, all of these gravitational stuff, it could be explained. And not just that, Einstein even predicted a lot of new phenomena based on his general theory of relativity, which is kind of mind-blowing really. And the thing is that, and the thing about general theory of relativity is that I don't know if it's actually not a drawback, but the thing is that general relativity is a very rigid theory. What I mean by rigid is that if I slightly change the equations of the theory, then the theory is destroyed. I mean, you cannot, the theory is not flexible. That is what I mean by rigid. For instance, in Newton's theory, it's there is the inverse square law. It's the force is proportional to 1 over r square. R is the distance between the two bodies. But Newton could explain why. I mean, it is possible to make some alternative versions of Newton's theory where maybe force is proportional to 1 over r cube, but still the theory would more or less work in some cases. But in Einstein's theory, this r squared law, this 1 over r squared, this inverse square law, it's a direct consequence of the geometry of space-time, and you cannot change this. If you make it 1 over r or 1 over r cube, then the theory gets destroyed. The theory will no longer give you the prediction. That means Einstein's theory is rigid. There are not a lot of modifications you can do. It's almost a complete theory in its own domain. It gives more or less a complete description of gravitational phenomena, except in some special cases when the modifications demanded by quantum mechanics become significant. That is, say, inside the singularity of a black hole or near the Big Bang, and that those are the things which are the topics of interest even today. Even today, we don't know the exact description, and that is what we guess. A theory of everything will give us the answers to those questions. General relativity alone will not give us. Okay, so now let's move on. Now, so Richard Feynman once remarked that. See, there are a lot of examples in physics when the same theory can have more than one mathematical descriptions, can have more than one, not just mathematical descriptions, can have more than one theoretical framework. For instance, in quantum mechanics basically studies possibilities and probabilities. Quantum mechanics is fundamentally a statistical science. It's because at the quantum level, at the level of fundamental particles, atoms and molecules, you cannot have definite, you cannot ask the question like, where is this particle, like you can do in Newtonian physics. You cannot have a fixed trajectory of the particle. You cannot predict the motion of the particle with 100% certainty. You can only say what is possible and which possibility has what percentage, what probability of occurrence. That is all you can do in quantum mechanics. But there are some laws the system, any quantum particle system follows, and these laws, that is what quantum mechanics is all about, right? But the thing is that there is one description of quantum mechanics which is called Heisenberg's matrix mechanics, and then there is the equivalent description which is Schrodinger's wave mechanics. Both of these descriptions give you the same results, the same eigenvalues, the same outcome, and both of them are mathematically equally correct, but they are different, fundamentally different, not fundamentally different, but they are different perspectives, different descriptions of quantum mechanics. So in matrix mechanics is kind of a mathematical theory, but wave mechanics is a more there is some concept of visualization and stuff in wave mechanics. So the thing is that what Feynman said is that he believed, and I think it's a very good point, that the very fact that we can have more than one possible description of the same theory, the same phenomena in nature, it means that the universe is fundamentally described by a simple and single theoretical framework, which in layman's term we call the theory of everything. Because all of these descriptions, they are just different manifestations, but fundamentally they are describing the same phenomena. So it's kind of the same underlying pattern, if I say in very rough layman terms. Okay, the next point I would like to discuss in this video is that, so then basically, see, I discussed the development of general relativity, not the development, just very rough. I've made some previous videos about the concepts of GR, like how it was developed, how Einstein got the idea that curved spacetime could correspond to the bending of light and gravity. But I'll not discuss all of this in this video. But this video is just a rough overview about physics in general, not just general relativity. And anyway, general relativity is not my cup of tea, So basically, I'm a physicist by heart, so I am interested in all of this, and any theoretical physicist should have a good understanding of GR, general relativity, but I'm more into quantum mechanics, quantum field theory and this kind of stuff. Okay, so anyway, let's move on. The next thing is that, so quantum mechanics, the development of quantum mechanics is a bit more complicated because general relativity was developed only by Einstein. He took the help of a lot of mathematicians and stuff, but it was almost, the major part was done single-handedly by Einstein. But the same cannot be said about quantum mechanics. It was developed by a lot of physicists, and it's very confusing theory because Quantum mechanics challenged our GR also modified our worldview, but quantum mechanics demanded radical modifications on our basic notions about the nature of reality, and that means, and that's why some physicists couldn't accept it easily, because quantum mechanics said that everything is fundamentally random and probabilistic. There is no certainty in physics and all of this. So it's a lot of complicated story, and some physicists accepted, some didn't, and it developed over many years. It's not an overnight development. No successful theory is an overnight development. But the thing is that quantum mechanics describes the three other forces of nature: the electromagnetic, strong nuclear, and weak nuclear force, in the framework of quantum field theory. Quantum field theory takes into account special relativity. Okay, it is in perfect agreement with special relativity, and it also takes into account quantum theory, obviously, and that is why it's basically a field theory of quantum and special relativity, kind of. Of course, field theory is a very technical term, but I cannot explain the mathematics of field theory, what I exactly mean by a field theory. But basic idea is that quantum field theory says that all the particles, actually they are not particles, they are just vibrations in a field. There are fundamental quantum fields associated with it. But what I mean by field is that it's, roughly speaking, it's kind of a field which is permeate. I mean, it's present throughout the universe, and it vibrates at some specific particular frequencies. There are mathematics which describes all of this, but I'll not be discussing all of those here in this video. And then there are more. Of course, the story is much more complicated than how these particles get mass. There's the Higgs mechanism, Higgs field, and everything. But let's keep it for another day, guys. And the thing is that so in quantum field theory, basically a force is just the exchange of a particle. There are two types of particles: fermions and bosons. Fermions are what makes up the matter, like electrons, quarks. Quarks make up the nucleus, and together they make up the atom. They're all fermions, and they have mass. I mean, rest mass. But bosons, like photons. Photon is the quantum particle of light. So if a photon is exchanged between, say, two electrons, then the electrons will repel, and the repulsion of charged particles falls under electromagnetic interaction. So that means this force, which we call the electromagnetic interaction, it's a result of exchange of a boson between two particles, between two fermions. By boson I mean the photon. Photon is a type of boson. So bosons are those particles which are responsible for the mass. For generating the forces. So these three forces, which quantum field theory takes care of, they can be described in this theoretical framework by the exchange of particles. But unfortunately, gravity, we have not yet been able to find such a description, such a mathematical framework or description of gravity. Gravity is in stark contrast to the three forces, and gravity is described by Einstein's general relativity, which is an entirely different theory. Where is the difference? Actually, you can understand this. You don't even need to know the advanced mathematics. See, in general relativity, basically the space-time is curved. It's a geometric theory. Space-time is curved, and the bodies are moving in the curved space-time, and that is how their motion is getting affected. And the presence of the massive bodies, they also affect the curvature. So basically, this is what we physics students, we call this background independence. General relativity is a background independent theory, and it's a good thing. Because what I mean by background independence is that the background of the theory, I mean this entire kind of this space-time continuum, or the entire stage where this drama is taking place. By the stage I mean the universe. It's independent. I mean, you don't need to specify the conditions that there should be a fixed background. These are the conditions. There is no initial there are no extra assumptions in the theory. You can predict the nature of the background, how the background will change, how the background will behave to the presence of mass, and you can also predict the motion of the massive bodies in response to the change in the background, change in the curvature of space-time. That is the beauty of general relativity, and that is why the theory is also a rigid theory, like I already said. But the thing with quantum field theory is that quantum field is also a very successful theory. I recently worked I recently studied quantum field theory in a bit detail, and I recently worked in, as some of you know, I worked in a fellowship project at PRL, Physical Research Laboratory, Ahmedabad, and my topic was it was more mathematics, but actually the application is on quantum field theory. And what I found was that it's actually a beautiful theory. It actually explains a lot of phenomena, and it has been verified experimentally, all these particles and all this. Even we have been able to predict new particles and later detect them in the laboratory, I mean in these particle colliders, particle accelerators. But still, what I feel is that I shouldn't be saying this, because I myself am a quantum, I work in my field, but still what I find is that general relativity, Einstein's theory, has a kind of beauty which is unmatched by quantum field theory. Because in quantum field theory, it's not a beautiful theory, it's not a mathematically elegant theory. But quantum field theory makes a lot of successful predictions, it has a very good mathematical framework, but it's background dependent. By that I mean the background is fixed, right? I mean, we assume there is a fixed background, because if we assume the background changes in response to these particles, then the mathematics is, I mean, we cannot develop the theory that way. The starting assumption is that the background is fixed, and in the fixed background, some particles are moving, interacting, and then we can describe these particle interactions and all. It's a pretty successful theory. If by successful theory you mean it has been verified experimentally and all those things, and it has a good predictive power also. Then it describes 3 forces, but Einstein takes care of only 1 force. But it's not beautiful. It's not, because it has a lot of assumptions and it has a lot of free parameters. For instance, a standard model, the standard model of particle physics, which is kind of, it comes out of quantum field theory. In standard model, basically you assume, see, there are some symmetries which you assume. Symmetric group, what I mean by symmetry is that it's not like in high school, like we have a circle which is symmetric, we have a sphere, even if I mean, of course, those are examples of symmetry, but mathematically, by symmetry, we mean that if we transform some object, I mean, if we change it, it could be a rotation, it could be anything, not just rotation or not just even translation. What we mean is that if we transform an object, then it's not like the object doesn't change, nothing changes, but some aspects of the object remains unchanged, and this is what we call invariance. And this is what we mean by symmetry, that then that particular aspect that is symmetric with respect to that transformation. And mathematically, to describe symmetry, we have something called group theory. There are symmetric groups, like there are different kind of transformations under which some particular aspect remains symmetric, and the group of all such symmetric transformation forms the symmetric group of that particular object. And so basically in standard model, we describe the 3 forces using symmetries like, SU2, SU3. SU means special unitaries. So some of you must know what matrix, just high school level knowledge. And then there's something called the unitary matrix, and special unitary means, suppose if we have a unitary matrix whose determinant is 1, so then these kind of matrix, and say if you're in 3, then it could, SU3 means it's a matrix of order 3. Then so there are a lot of meanings. Actually, what I mean by matrix is that, I mean, at high school we just learn matrix as a mathematical idea, whatever tool, whatever, but in physics, matrix denotes some transformation. Suppose we have this rotation matrix. So if you multiply the rotation matrix with a column matrix, suppose 2 by 2 rotation matrix, it's a square matrix, and a column matrix is just 2 elements, up and down. So that column matrix basically denotes a vector in some space, and that basically it could mean a particle, it could mean anything. And if you multiply that with this rotation matrix, 2 by 2 square matrix, then you see that you get another vector, I mean a column matrix, that basically describes the position of the particle after the rotation. Suppose initially the vector was at some point, after the multiplication with the square matrix, you get the vector at some other point. So basically, these matrices in standard model, they denote some rotation, some transformations. But of course, these are not simple geometric transformations like, just simple rotation or anything. They're very complicated transformations. And this is how we can describe. That's just giving the basic idea. I'm not going into the mathematics here. I mean, for that you need to know how the Lagrangian of a particle is defined. It's very complicated. I'm not going into that here, guys. The thing is that that is the thing about standard model. But suppose you want to know the mass of some particle, then the standard model will only give you a range, and the range is correct. It gives you the correct range, but it does not tell you the exact value of the mass. Then how can we say it's a successful theory? How can we say it is verified experimentally? Because in standard model, it's not a rigid theory. There are a lot of parameters in standard model which can be changed, and it has been found out that if we appropriately adjust or tweak these parameters, then we can make the theory, we without disturbing or without destroying the framework of the theory, we can make the theory give us the correct value. I mean, so that means, yeah, technically it gives the correct predictions, but it's not mathematically beautiful like Einstein's theory. When Einstein made the prediction that this star will be like moved by this angle due to the solar eclipse and all those many more predictions of general relativity, he didn't make any assumption. It all came out right out of the theory, right out of the mathematics of general relativity. So anyway, it seems like I myself work in quantum field theory, but I am praising general relativity a lot. Okay, I mean, it's a praiseworthy theory because Einstein singularly developed it, no doubt about that. But let's not turn this video into GR versus QFT, general relativity versus quantum field theory. Let's move on. Now I'm moving to the last part of the video. Now I'd like to discuss one last point of the video, and that is that. So general relativity, we understood the basic difference. Now, so what is the problem? Problem is that this is a fundamental problem in theoretical physics today, that we have not yet been able to satisfactorily reconcile or kind of explain all the 4 forces in a single theoretical framework. On one hand, we have quantum field theory, which takes care of 3 forces except gravity, and on the other hand, we have GR, general relativity, which takes care of gravity. Now you may ask that, so have people not tried? Of course they have tried, and they have even proposed successful theories, but we cannot say that these theories are 100% correct and all. The best candidate we have which kind of combines these 2 theories is probably string theory. So what is string theory? Look, string theory is something I want to work in the future, but to be very honest with you, I myself don't know the mathematics of string theory. It's actually, you will be surprised to know, even the string theorists who are working, the pioneers of the field like Edward Witten and all, even they have not been able to figure out the equations of string theory. It's such a complicated theory mathematically, but it's still actually, I shouldn't say it's complicated. It's more like it's it's a beautiful theory. Mathematically, it's a beautiful theory, but we understand very little of it. Like Edward Britton said, that string theory is probably a part of the next century physics, which accidentally fell into our century, and we cannot make sense of it. And if Edward Britton cannot make sense of something, then I mean, who are we in front of him? Anyway, like, so basically, what is the idea of string theory? See, where the problem arises. See, so you may ask, like, okay, quantum field theory says that all these forces, they can be described by the exchange of particles. So if I assume that there is such a particle for gravity, there is such a theoretical assumption there. We call it the graviton. It's the boson for gravity. Then what's the problem? But it has been found out. Like, see, quantum mechanics comes into consideration. See, when you are trying to find the velocity of a football or a car or macroscopic objects, you use Newton's law. You don't use quantum mechanics. Technically, you can use quantum mechanics. Quantum mechanics will also give you the correct result, correct predictions, but it's very complicated. I mean, we don't need to use quantum mechanics because these are heavy macroscopic objects and these are big objects. It's not a small atom or electron. So quantum mechanics comes into play only when we go to fundamentally, when we go in the quantum realm, in the realm of atoms, electrons. I mean, the size is very small, right? And the energy is very high, because at such small scales, we are dealing with very high energy. It's different scales of energy, very high energy of the order of, I don't know the exact order, so let me not make any mathematical statement, but very high energy, right? Then what about gravity? Gravity deals with, you see, astronomical distances, say very big objects, planets, galaxies, stars, and they are separated by a huge distance, light years. But in quantum, two electrons maybe, that is what quantum is about, at small scales, and gravity is about large scales. So yeah, Einstein's theory makes correct predictions about the large scale world, the universe, the large scale structure of the universe, and quantum mechanics makes correct predictions about the small scale structure. But suppose if we have some certain phenomena where both of these theories become significant, like what can be such a phenomena? For instance, we could have, say, inside the singularity of a black hole. So inside the singularity of a black hole, or maybe say at the Big Bang. So at the Big Bang, it was a very, Big Bang means the universe started from a single point, Big Bang, right? And since it started from a single point, since it started from a single point, that means when the universe began, if we assume the Big Bang theory to be correct, then it was a single point, very small. So quantum mechanics is significant there. It's not a huge distance. So we have to take into account quantum mechanics, right? So, but see, quantum mechanics is significant when the universe started in the Big Bang. But gravity is also significant because it's a very dense point. It's a very dense. That means basically the gravitational interaction is the same thing happens inside a black hole, the singularity of a black hole. When an object collapses into itself and it's very dense. So basically there are some points in the universe which we mathematically call singularities, like inside a black hole or in the Big Bang, where both quantum theory and Einstein's theory, gravity, both of these become significant. So when we deal with those theories, then we cannot. Yeah. So as I was saying, so there are some examples where both gravity and Einstein's theory become significant, and in those like in the singularity, in those areas and those regions of space, I mean, nobody has observed, but yeah, it's a mathematical prediction. So for those cases, general relativity does not work, and quantum theory alone also does not work. We get nonsense results. So to explain what happens deep in those points or beyond, we need a theory of everything. We need to combine both of these theories, and that is what string theory does. So basically, what is the problem? See, if we go deep down, then the question that arises, that is there any smallest possible length? How close can two particles get, or all these kind of questions we consider. Basically, string theory gets around the problem of singularity by saying that fundamentally everything, all these particles, all particles, whatever you say, if we go deep down, fundamentally they are not particles, but they are strings. Say you have a rubber band, so it's a closed string, and closed strings correspond to gravity. But then you can have suppose if we tear the rubber band, then it's an open string. So these strings are deep down every particle, and these strings are vibrating at some frequency. Kind of same concept like quantum field theory, but the mathematics is different, and the very structure is different, because in quantum field theory it's a field which is vibrating, but here it's a string which is vibrating. And this vibration of the string is the same thing fundamentally. But if the string vibrates at some particular frequency, suppose it gives us an electron. If it vibrates at some different frequency, it gives us maybe a quark or some other particle. That is the beauty of string theory. Fundamentally, everything is a string. Now, the structure of the string, whether it's a closed string, whether it's an open string, all of this matters. But of course, let's not go deep into it here. But since it's a string cannot be confined to a single point. You see, that's, roughly speaking, that's how string theory gets around the problem. And it's not just that. String theory is not like an idea, like some physicists said that, okay, so let's just assume it's a string and let's just develop the mathematics and we have a theory. No. string theory was initially developed as a theory of the strong nuclear interaction, but then it was found out rather accidentally that string theory requires gravity to be included. What we are trying to do for so many years, so many decades, string theory naturally, as a requirement, gravity must be included in string theory. And then people started thinking that, so maybe is this the theory of everything that we are looking for, that Einstein couldn't find for 30 years? And then people were hopeful. And yeah, but the problem with string theory is that it's very difficult to devise an experiment which will verify string theory. And until we have experimental evidence, a theory cannot be called a scientific theory. I mean, of course, you see, there are some experiments which, but the thing is that even if we get the result we desire from the experiment, then it could mean string theory is true. But even if string theory is not true, even then we could get some result. There are a lot of possible explanations. So it's not a unique or conclusive experiment. That is the problem with string theory, that lack of experimental evidence, experimental support. But yeah, string theory is a finite theory. It's a finite theory and it's mathematically consistent. Everything is fine. No issues there. But yeah, there are some problems. Like, there are many different versions of string theory. Edward Witten did a great job by combining the different versions of string theory into something he called the M theory. But in string theory we assume that there are a lot of dimensions, right? String theory doesn't work in 3 dimensions and just if we include time 4 dimension. Initial versions of string theory, they require 10 dimensions. Then some older versions require 26 dimensions. And then Edward Witten said that to combine them, you need to assume that there are 10 dimensions of the universe, but the string itself is 1 dimensional and it's vibrating. It has its own dimension. So basically it's an 11 dimensional theory. The mathematics is a bit complicated. Even I myself don't know the exact mathematics, so let me not talk about it. But yeah, the basic idea is that now you can ask that, okay, so if there are 11 dimensions, 10 dimensions, why can I only move in 3 dimensions? In 3 dimensions, just forward, backward, up, down, and left, right. Why not? What are the other dimensions? So yeah, it was proposed that maybe the other dimensions are curled up very tiny in a very small space. Because see, if I see from very far away, if I see a rope and an ant is moving in the rope from very far, the rope is appearing like a one-dimensional line to me, and the ant can only move in either forward or backward. But if I go very near to the rope, I'll say that it's actually a cylinder. The shape of the rope is actually a cylinder. It's 2-dimensional, and the ant can move forward and backward. But if it wants, the ant can also move like this along the circumference of the rope, right? So basically the degree of freedom of the ant is more. But for that I need to see it from close. Now that means if suppose there are 10 dimensions, so if the other dimensions which we cannot see with our naked eyes or even with our microscopes and all of our technologies, maybe they're curled up to very tiny dimensions. But string theory requires that all of these dimensions are present everywhere, even like everywhere in space, in front of me, everywhere in space they are present. It's not like they're present in some particular region in space. But the thing is that we cannot access the extra dimensions, but these dimensions are accessible to the strings, and it must be, because otherwise the mathematics of string theory will not work. So yeah, string theory is kind of, it might seem like a science fiction kind of thing, like higher dimensions and all, but it's actually, and then there is no experimental support. So that's why a lot of physicists don't take it seriously. But I think it's a beautiful theory. But whether it is the theory of everything, we don't know yet. That remains to be seen, of course. Then there are some other alternatives to string theory also, like say loop quantum gravity. Loop quantum gravity is not actually, see, string theory kind of explains all the 4 forces in the same framework. But loop quantum gravity, what it does is that it kind of, like, see, then there is a question like whether we should try to find a geometric description of quantum field theory, like just like general relativity, or we should find a quantum field theoretic description of gravity, like whether general relativity prevails or quantum field theory prevails. Then all of this gives rise to different alternatives, different hypotheses. But like string theory, loop quantum gravity, then there are even more exotic new theories which are being proposed. But yeah, most of them are not yet developed to a very great extent. So they are not yet I mean, we cannot talk about it yet because they're not yet developed. Like string theory is still a developed theory. I mean, we don't know a lot, we don't know maximum, but still it's a developed theory. It's well studied and everything. Now finally, so I discussed the total history of physics with you in very brief. Last thing which I will discuss with you, last point, is that so all of this which I told you, quantum theory, string theory, basically it's a kind of we try to find out what is everything made of fundamentally, fundamental particles, fundamental forces. And our assumption is that if we can explain what the universe is fundamentally made of, then we can explain everything. But the thing is that suppose we know the theory of everything, we know how all the particles in the universe works, we know how all the fundamental forces works, but we know this at the level of the individual particles. But if I know this, then can I explain some complex phenomena like consciousness? Technically, you know that how all of the atoms in my brain, all of my electrons, neutrons work. You know the theory individually, but can you apply this theory to explain how Arpande is speaking, how Arpande is thinking, what Arpande will do in the next second, or any human consciousness, not even consciousness, even there are a lot of complex stuff happening all around us, fluid mechanics and a lot of things. Consciousness is an extreme example, even not consciousness. Most likely you cannot. Some people say that it's possible in theory, but of course the mathematics becomes too complicated, because you can know what how two atoms will interact, but if there are billions of atoms, trillions of atoms, then it becomes very difficult. Even if we know the fundamental laws, we know the fundamental theories, but for that knowledge alone is not sufficient. But the thing is that this gives rise to something called complexity science, which is a comparatively recent development. I mean, compared to all this quantum and all, it's a recent development. So approach of complexity science is different. I mean, it's all related. You see chaos theory, complexity science, they assume that the laws of complexity are universal. I mean, the laws that apply to any complex system, be it consciousness, or be it the birds flying in the sky in a particular pattern, or be it the galaxy formation, or be it something abstract like the rise and fall of stock market, the stock prices, even economics, finance, and all of these things, the pattern, the basic governing principles are the same. And yeah, chaos theory is a very successful theory, lot of predictions and lot of things we have observed. Now the question I would like to address is that some people say that we need some fundamentally different description of to explain. See, it's all very well if we know the theory of everything, if we someday discover the theory of everything, something like string theory or maybe something else, whatever, then we have a good description of all the particles and forces at a fundamental level. But what some people claim is that even that is not sufficient if we want to find out, if we want to explain the world around us, this complex stuff which is happening like consciousness and all. For this we need some, there are a lot of new developments like assembly theory, constructor theory, and chaos theory is not new anyway. But yeah, all of these kind of systems which study complex systems, science which studies complex systems. And the beauty, I mean, the thing is that some people are pessimistic. They say that we can never understand these complex phenomena. We need some fundamentally new kind of laws which we may or may not discover, but we can never understand them just by using the known laws. But I am hopeful about the future. See, if we consider the future of theoretical physics, the last few decades progress is not very inspiring. Progress is not very promising because there has been no significant development in the field of theoretical physics. Experimental physics, applied physics, discovery of Higgs boson in 2014, I guess, then just a decade back, then this artificial intelligence, machine learning, every day we are hearing about new breakthroughs and all, but fundamentally we have not discovered anything new since the discovery of the standard model. Yeah, string theory and all, but they have not been verified. But so that means that's why people are pessimistic, and I am also a bit pessimistic. But then there are some other issues like funding problems and all, but those are human created issues, and I will not discuss any human created issues in like funding problems and corruption, or the influence of money in the field of science and research. I will not discuss this in this video, but still I'm hopeful about the future of physics, because I feel like, see, right now it appears like, okay, these are very complex stuff, billions of neurons, how can we explain consciousness? But one thing is that if we try to think of it like this, for instance, a vector space, which we all learn. What is a vector space? In very simple terms, it's what do you mean by space in mathematics? It's not like any, I mean, if we were to explain vector space to a, say, high school student, what he will say without going into the mathematics? I mean, anyway, the laws, the mathematical rules of vector space, associative, this commutative law, then there are these laws, then the laws of the scalar multiplication, then these laws are pretty simple. Even a class 7 student can understand. So understanding the rules of that a vector space follows is simple, but applying those rules and predicting the behavior of a vector space and building a theory based on a vector space, that is, of course, that's extremely difficult, because otherwise vector space would have been taught in high school, right? But it's not taught in high school. It's not even taught in advanced courses, in a lot of advanced courses. So, so basically, vector space is a group of vectors and scalars. By group, I don't mean a group as in group theory, because the conditions that a group need to satisfy mathematically, they're not the same conditions that a vector space need to satisfy. But yeah, it's kind of coming from a, there is a field. Suppose if I define a vector space over the field of real numbers, then real numbers act as the scalars here, they're the field, and then the vectors, they act like the elements of the vector space, are the vectors. So vector space have two types of elements, vectors and scalars. And the scalars, we can define the scalars with the field, and we can also define the vectors, whether they are defined in their real numbers or complex numbers, they are defined in the real space or complex space, whatever. But if we know all of these, then is that all a vector space is? Is that enough? I don't think so. Yeah, so as I was saying, so to understand what a vector space is, it's not enough to know the elements, know the properties of the scalars and the vectors that comprise that form the vector space. You also need to know what are the rules that they follow, and these rules do not change. For any collection of scalars and vectors to qualify as a vector space, they must follow certain rules which I was talking about, and all of these rules, they are the same for all vector space. These rules do not change, and you need to know these rules if you are to know all the properties and everything about the vector space. So basically, what I was saying is that these rules kind of act like a constraint to the vector space. Yeah, a vector space has a lot of vectors and a lot of scalars, but they cannot just behave in any way they want. Any transformation, by transformation I mean it could be addition between vectors, it could be multiplication between a scalar and a vector. Any such kind of mathematical operation must follow these rules. These rules kind of act like a constraint. So in the same way, the system which we're trying to describe, very complex systems, say millions of billions of parts, suppose these parts are vectors, I'm just giving a rough analogy, right? Then probably we can find out in the future, or even now we know that some rules they follow, some constant, but in the future maybe we can find out even more universal rules that these parts follow. Suppose by universal rule I mean it's not just a rule between just two parts of the system. All the parts of the complex system must follow these rules. So if we can find out such rules, such constants, then even if the system is a complex system consisting of billions of trillions of parts, even then the description of the system will be simple, because the mathematics of the vector space, it's not, I mean, I won't say it's simple, but it's not that complicated. The rules are the same, they follow the same rules. It has the same specified structure. Any vector space, there are a lot of possible vector space. We can have a 4-dimensional vector space, we can have a 5-dimensional vector space, we can have an n-dimensional vector space, we can even have infinite dimensional vector space mathematically, we can have vector space defined over the real field, over the complex field, but all of them, they follow some specific laws, specific properties. Of course the result is different for different cases, but the basic laws don't change. Now why am I hopeful about the future of physics? Because even though there have been no such development in theoretical physics, there has been tremendous progress in this field of complex physics, complex systems. And two things which I am hopeful about is that number one is that this fast growth of technology and artificial intelligence and machine learning algorithms, they might help us run very good simulations of complex systems and might help us discover some universal rules, universal laws about complex systems. And once if we can find out some universal rules of a complex system, then even if it's a very complex system consisting of a large number of parts and apparently the behavior is unpredictable, then maybe it will be easier for us to find a mathematical description of the system and find it. And then, now think about it, we are trying to go from bottom up, right? We're first trying to find out the fundamental theory of everything, and then we're trying to build up our theories and describe complex systems just from a knowledge of the fundamental particles. But if we can somehow first understand the complex system, and if we try to go top down, if we try to go down and try to verify if our knowledge of complex systems, if that theory somehow leads us to the fundamental theory which we already have, the fundamental particles and interactions and all those theories, then it will be a remarkable verification of all our theories at all levels, and then we can confidently say that yeah, now we actually have a theory of everything, not just 4 forces and just the particles. By everything I mean everything, be it a very complex system like consciousness, or be it a very simple system like a single electron free particle. I mean, of course this is the ultimate goal of any physicist, any scientist rather, because technically if we have a theory of everything at all levels, then technically we can predict the behavior of any complex protein, any complex molecules, biochemistry. It will, all of fields, not just physics and mathematics, will have repercussions in biochemistry, in even probably even psychology and social sciences, finance, economics. Everything will be, all the studies of, I mean, human knowledge will enter into a whole new level. But of course that is the goal of, that is the ultimate goal, and of course we are not going to reach there anytime soon. First let some group find out the fundamental theory, and let some other group work in complexity physics, and some other group work in maybe artificial intelligence and everything. I mean, it's a very far dream. So anyway, the point of this video was that is why see, it's a very interesting thing actually, because sometimes we think that if we just have a collection of data, then we understand everything about it. It's not that. Just like the collection of data, the data is important, but it's also important to know what is the relation between the data. Like there's a simple example, let me give you. Suppose I have, just assume I work in some corporate company, and suppose I am say director or some partner or whatever, and my juniors, people who are working under me, suppose I give them a project that you make a presentation about, suppose some big hospital has given me a job that I want your company to take care of the digital system of our hospital, like a record of all the patients who are getting admitted and everything. So I give my juniors a job that you make a presentation which you will present in front of the manager of the hospital, and then if they are satisfied, they will give us the project. So yeah, maybe assume it's a very big hospital, a very high top rated client. So suppose they have some data, they get some data. By data I mean, say, in which month how many patients were admitted, how many beds are empty, or how many patients could not be admitted due to non-availability of beds. So this is what I mean by data. Like data means like how many patients were admitted, how many beds are empty, how many beds are full, all this thing. So suppose they randomly generate some data. Like suppose, like why am I giving this example? Because this way you can understand that data is not important. More important is the relation between the data. So suppose the data says me, they just randomly pick some data just to give me an example of the presentation. Like I'm not doing this final presentation in front of the hospital manager, just to give an example. But suppose the data is telling me that in the hospital some beds are empty in the month of, say, May, but in the same hospital some patients could not be admitted in the emergency according to the data, right? If you just look at the data, you will not find out. But if you analyze the data, you will see that suppose 3 patients could not be admitted in the emergency due to non-availability of bed, but at the same time there are not all the beds are not getting filled. So suppose if your data gives you this, then clearly it's an incorrect data, because the relation between the data, it's not the logical relation between the data is not getting satisfied. Because if you have empty bed in the hospital, then why are you not admitting the patients in the emergency? It's a contradiction kind of. So similarly, if you just know the parts of the complex system is made of, but you are not taking care of the relation between the parts and everything, then basically you are not, then that is not enough if you want to predict the system. That is why I gave you the example. Same for vector space. If you know the elements the vector space is made of, that was, suppose it's a real space, two-dimensional space, so it's made up of two-dimensional vectors, real vectors, maybe the scale, and then the field is the real number, or whatever you define, however you define it. That is a part of it. But if you don't define the properties that these different vectors and elements must follow, then your description of the vector space, or analogously your description of the system, is not complete. So yeah, now, so basically the point of this entire video was just to give you an idea about, just to give you a rough overview about the development of physics, and more importantly how physics will develop in the future. Because in the past, physics, we built all our theories on the assumption that this kind of basic assumptions, but now in light of complexity, size and everything, we need to take care of a lot of things. And what I'm seeing is that recently, and it's very beautiful, that if you think about these things deeply, then you will understand at some point of time, you realize that ultimately it all merges into one. Be it physics, computer science, finance, economics, even chemistry, mathematics. You see, they're different subjects, you feel like, but ultimately the logical framework, if you think deeply, you see that all of this, they are kind of, at one point they are kind of merging into one. And then you see the interconnectedness of all of science, and that is the beauty of science. That is when you say that no, I'm not a physicist. I may have a degree in physics, I may have a degree in mathematics, I may have a degree in chemistry, but by heart I am a scientist. I am a searcher of truth. I want to find the truth of the universe. That is what I want to do. I will not, say, when people ask me that who are you, what do you do for a living, I will not say that I'm a PhD in physics, I'm a professor of physics, I'm a professor of chemistry. I will say that I am a seeker of truth. I am a scientist. That is when you will say this, because everything is interconnected at some point. And you see, the more you will understand this more, we all of humankind will understand this more if we find a theory of everything. Then we'll realize this even better. Like Stephen Hawking said, his famous book, A Brief History of Time, at the end of the book, he finishes the book with this statement: like, a theory of everything will not just have an impact on the mind of a few scientists. It will, over the course of time, it will affect everyone, from ordinary people to scientists and even philosophers. And once we find out the theory of everything, then we can all, scientists, philosophers, and just ordinary people, then we can all take part in the discussion of the question of why it is that we and the universe exist. Now we're moving to the next level. Theory of everything will tell us, will answer how the world works, but it will not answer the question why the world exists, like why the universe was created, what is life. These questions we don't have an answer. Yeah, some people will say that philosophy have an answer, nihilism, metaphysics, but those things are not verified. So I won't say we don't have an answer for sure. Maybe philosophy has some suggestions, some proposals. But yeah, if we have a theory of everything, then maybe we can all take part in the discussion of the ultimate question, that why we exist in the first place, why the universe exists. And if we find the answer to that, then that will be the ultimate triumph of human reason, because then we will know the mind of God. By God, I don't mean some conscious creator, some supernatural deity who created the universe. By God, I just mean the ultimate laws of nature, or the ultimate simplicity, ultimate order in the universe. Amidst all of this apparent chaos, apparent randomness in our theories, and even if we shift our gaze beyond science, the apparent chaos in our surroundings, humans killing humans, and all this cruelty, all this, all this, I mean, what to say, all this what is happening in society. That's why I say, like, I'm really, I don't really like humans. I mean, like, right now I'm shooting this video in a place called Dooars. It's in North Bengal, and it's actually this is right now I'm in my resort, and it's in the middle of a jungle. Just a couple hours back, an elephant came in front of our fence. I just, and then we, it's a very good place, and we just, you can do a lot of jungle safaris, and then you can, there are a lot of waterfalls, rivers, and you can get, it's in the very lap of nature. I mean, it's the best you can get in India, in my opinion. Of course, if you go to some foreign places, it's more exotic, it's more beautiful. So basically what I realize is that sometimes it's important to take a step back and admire nature. It's fine, all of our college work, all of our job, all of our this technical stuff, it's fine, it's important. But sometimes it's important to take a step back and forget everything, forget who you are, what is your identity, what you do, what is your degree, everything you just forget, and you just enjoy a few days in the lap of nature. I mean this is actually bad, because when I will go back to Kolkata, to my hometown, it's a city, it's a big city, then I will be at a worse position than when I came, before I came here, because it's here, this place is paradise. But when I go there again, I mean it's better not to come to paradise if you cannot stay there forever. If you're going to paradise for 6 days, it's better not to go at all. But anyway, I came here because right now we have a holidays, and I came with my parents. I'll be posting some more videos about this place also. You keep an eye on my YouTube channel. But anyway, I'm digressing from the original point of discussion. I don't know how many of you are still listening. It's already 46 minutes. But yeah, I know some of you are. So basically, that's what I realized. Like all of this, the reason for this is that what I feel like is now this is not science. If you're here for the physics, you can just stop watching the video from this point. But if you're interested, you can. I'll talk for 5 or 6 minutes more. Okay. So basically, what I feel is that the reason for all this chaos, and at human level, all this cruelty and all, I think because humans have lost sight of their ultimate goal. When during our hunter-gatherer ancestors, when humans first came in Earth, they only cared about survival. They only cared about, they hunted, and they lived in jungles and all. And then slowly we we became civilized. We learned agriculture, we learned industry and all. But once our basic needs, food, shelter, and all of this were satisfied, humans started thinking about the world around them. Why is the world the way it is? And that is how science, physics, all of this developed. But right now, I think I don't know. It's probably because of the influence of money in people's life. Because because ultimately, like it or not, power is money. Money is power, and a lot of people who have that power, who have money, they are not good people. They don't have good intentions. So I don't know if that could be one reason. There could be many other reasons. I'm not a social scientist. I should not make any statement. But what I think is that humans have lost sight of their ultimate goal. That we are here for a reason. We are here to find out the truth of the universe. No, they just think too much about petty matters. For money, for power, they become even more cruel than animals, of course. And then, so I think that is what when I read Stephen Hawking's book, this last paragraph, I think this is what he had in mind when he said that once we find a theory of everything, then maybe all of us humans, regardless of whether I'm a scientist, or whether I'm just a businessman, or whether I'm a philosopher, or whether I'm just a beggar in the roadside, maybe all of us will come together. Maybe a theory of everything will also unite, will bring all the human beings closer, and we will just understand that yeah, we are kind of our life. It's beautiful. We are here for a say yeah. So as I was saying, like so if we can all just for a moment admire our life, like our beautiful life, like we're just here for say 80 years, 75 years, and in this vast and endless mysterious universe. And even if we cannot find the theory of everything, even if we cannot understand all the secrets of the universe during our lifetime, but it's beautiful that we're even given the chance to wonder about these questions. Even that in itself is beautiful. And can't we just for a moment just think about this and just admire nature and admire life for what it is, instead of all this nonsense, all this cruelty, all this petty matters and all. And I think if we ever find a theory of everything, I think that will bring humans together, and that will once more bring in sight our ultimate goal, the fundamental nature of reality, which humans have lost sight of, it feels like, in today's currently. So that's all for this video, guys. I discussed all of all this stuff, the development of physics, future of physics, and in the end also I became a bit philosophical, which is characteristic of me, kind of. But yeah, I hope you enjoyed the video, and I also hope you enjoy the location. I mean, of course, you are just not present here physically. I'm present here physically, and I know it's a beautiful place. You will not get it if you are not physically present here. But yeah, I try to show you, and you can see it's in the moonlit night. You can see the moon, and you can see I'm in the lap of nature here. And so yes, guys, that's all for this video. Thank you very much.